Welcome back. It's time we show an example of a buffer overflow attack. Now once again, just to mention, for this specific lecture, you will need a little bit of knowledge of C programming, of assembly language, of how the stack works, and just a little bit of Python as well. If you don't know all of this, you can sit back and just observe and watch this lecture and try to understand as much as possible, and if this is something that interests you, feel free to learn more about it from the resources that I left in the previous lecture. Okay, let's see how hackers discover vulnerabilities. And keep in mind, this will be a rather simple example. This is usually much more complex, since the code is usually a lot bigger than the code that we will use. So you will notice right here on my desktop, I have two programs, vulcode C and vulcode 2C. So we are going to try to attack both of them. We will just show a simple example on the vulcode C. So let me just open the program so you can take a look at it. And this is pretty much the entire program. Okay, so it has two functions. It has the main function and the read request function. Now, if you are experienced with C programming, you will notice where the error is right away in this code. So let's go through it real quick. The main functions allocates a variable integer called x, and the value of this x is stored from the return value of the read request. If we go to the read request function, it allocates a buffer size 8. It also creates another integer variable, and then it calls this gets function. Any C programmer will right away tell you that this is a vulnerable function, and we're going to see in just a second why that is. After the value returns, it simply prints the number right here to the screen. So we can test this code. Let me just first remove the executables that I already compiled, and let me compile this code, vulcode.c, and output vulcode right here. Now, the compiler will give us a couple of errors, and you will see right away that it gives us a warning for this gets function. It says use fgets instead. Down here we can read, warning, the gets function is dangerous and should not be used. And the reason why it's dangerous is because this function doesn't check for the length of input. It asks for input from a user. The user can specify any length of input that they want, and then it will get stored in this buff variable, which is the size of 8. So if the user specifies a larger input than 8, then we have a buffer overflow, just because the developer used this gets function. Even the compiler says use fgets instead, which is a more secure version of this function that allows the program to check for the user input. Nonetheless, our program did compile, however, and if we run it, it will wait for an input. If I type 1, 2, 3, it will just print x equals 1, 2, 3, which is this statement right here. If I go, for example, a, it will just print x equals 0 because it did expect a number, but I specified characters instead. Therefore, it didn't crash the program, but it also gave some incorrect output. And finally, if I try to specify more than 8 characters, let's say this much, we get segmentation fault. The program crashed, and this is due to this buffer overflow that we have right here. Okay, so let's take a deeper look into this. And to do that, we need to use something called debugger. For this, I will use GDB, which is a debugger that comes with Linux. And if I just type GDB and then the executable program, it will open it in debugger. And now I can read it in assembly language. So let me just enlarge this a little bit. And there are different assembly flavors, so I'll just set this assembly flavor to be Intel first, and now I can try and disassemble the main function, which will be this function right here. So this is how assembly language looks like. Now we will not be explaining the assembly because that would take some time. I assume that you do know it for this specific lecture. Keep in mind you won't really need it for the rest of the course. And pretty much it simply just allows us to manipulate with different registers, move things from one register to another, access the memory, and all of that. We can even recognize some of the things from the C function. So for example, we have this call right here, and then it calls read request. So this is pretty much here in this line when the main function calls the read request function. This is pretty much that exact same line. Someone trying to analyze this code would notice that this is not a regular function, so we can also try to disassemble that one as well. So disassemble readRec, which is also a developer coded function, and right away anyone that is experienced will notice this gets function being called right here. And they would already know that there is a high percentage that there is a vulnerability in this code. So let's straight away break at this function, which essentially means that once we start the program, it will pause right before executing this function, and then we can go step by step to see how it executes and also to inspect different registers. So once I set the break at the read request function, I can type run and the program will start. I can straight away check my registers by typing I and then space R, which will show me the values of all of the registers right here. Keep in mind the RIP register is important to us because it is the instruction pointer. It points to an address where the next code will be executed, which is currently this address right here. We can even confirm that by once again disassembling the read request where we set our breakpoint, and it gives us this arrow, so this is the next instruction to be executed. We're currently in the read request function. If I type next, it comes to the point where it asks for our input, and remember, if I type something larger than the size of 8, which is specified in this code, we will get an error. If I type IR, we will see something rather strange. So RBP, which is the base pointer, has a bunch of 41s inside of it. That is because we managed to overflow it with these A's. Take a look at this image from last lecture. So this is pretty much how it works. This is space for our variable, or in our case for the buff. Then we have the saved EBP, or in our case RBP. One is for 32-bit and the other one, which is RBP, is for 64-bit. And after that comes EIP, or in our case RIP. So ideally we want to control the EIP. Now we need to calculate how much space our variables are using, and we need to calculate how much space EBP is also using. Then we will get to here, which is our EIP. Okay, so let's do that straight away. We know that we have two variables, right? Which is the buff, size of 8, and integer, which, if I'm not mistaken, is size of 4 in x64, and we can double check that by going to Firefox and typing size of int. Now keep in mind that different integer values can have different sizes. For example, there is short integer, there is long integer, and they will both have different values. Here we check the 64-bit size, we check the regular integer, and it's 4 bytes large. So we have 4 bytes of size for this value right here. And then we have the RBP, which is the size of 8. So all we need to do is put that together. So 8 plus 4 plus 8, and whatever comes next should be stored in RIP. Let's give it a try. So let's run the program again. We want to start from the beginning. We want to go to the next, and here is our input. Let's type 8 times A. This is for the buff. Then we will type 4 times B for the integer. Then we type 4 times C, or pardon me, 8 times C. And by the way, for those of you who don't know, the reason why here is 41, 41, 41 and not A is because A is actually the same thing as OX41. It's just in hexadecimal. So these are pretty much 8 times A. Now with this, we fill in the buff. With B's, we overflow integer value. With C's, we overflow RBP. And now if I type 6 times D, these 6 Ds should overflow the RIP. Let's give it a try. If I type I and then R, we see that C's overflowed RBP, and we also see that these, which are 44, overflowed the RIP. So we successfully controlled what we want in the RIP. Okay, now that we did that, which is the basic part, let's try to actually exploit it with volcode number 2. Let me just close this. I need to close this as well. And first of all, let's check what volcode 2 even is. So I will open it. It's a little bit of larger code. It has 3 functions, and our goal in this code is to run the win function. So it has the main function with a simple if-else statement. It calls if test password, which then allocates a password variable with a size of 10. It asks us to input the password, and it uses once again the vulnerable gets function to do that. So we already know that there will be a buffer overflow right here with this line, because the password is limited to 10 characters. If this function is called, and it's called in 100% of cases, then it will print fail. In other times, it will print win. So if you look at this code, you will notice that win pretty much never gets called. There is no path in code where win is getting called after a certain line. This if statement will always work, so we will never get to this else win statement. So let's try to hack this program and get to this win statement ourselves. We already can have an idea of how we can do that. We already know that RIP is the instruction pointer, and if we somehow get the address of this win function in the instruction pointer, we can perhaps run it. So let's give it a try. Now, in order to remove all the possible stack protections that we might have and that might present us the problem when exploiting this code, we need to compile it a little bit differently. So I will run gcc-fno-stack-protector, then -z, execute stack, -nopy, and then I will use the code, which is volcode2.c, and I will output it in volcode 2. This will compile. It will once again give us the warning for the gets function, saying that it's dangerous and that it should not be used and that we should use fgets instead. Now these compilers are good because they do give us this warning, but some compilers won't give you the warnings. Especially if you turn the warnings off. You won't really notice this. Now let's run our code to see how it even works. It asks for our password. This is just the memory address or random memory address. And here we can type test and it will say fail. We can type test123. It will once again say fail. So pretty much there is no correct password here. It will always say fail. But let's hack it using GDB. We open GDB volcode 2. Once again, I will set the disassembly flavor to be Intel. You don't have to if you don't want to. This is just personal preference. And now let's disassemble the main function. The attacker can go through the main function. They can see that a certain function called test_pw is being called right here in this line. They can then try to disassemble that specific function. And as with the previous example, they will notice that gets function is getting called and they would straight away know that this program is vulnerable. Okay, once again, we notice gets. Let's put a breakpoint on this test_pw function and let's run the program. We can check the registers to see what else do they have. So this is the current value inside of the instruction pointer, and we can confirm it by typing disassemble test_pw. It will point to the beginning of the test_pw function, since that is where we put our breakpoint. This is the address where it's currently at, or this current instruction. If I go next, it will ask for the password. Here I can type anything. So let's go with bunch of A's, or let's go with uppercase A's, just so we can get those 41s once again in the RBP. And we get the segmentation fault. Okay, let's check the registers. The RBP is once again overflown with 41s. So what do we need to do in order to get our desired value in RIP? Well, we need to first overflow the password value, which is the size of 10. So we will use 10 A's for that. Now, since this is the only variable inside of this function, the next thing that we are going to overflow will be RBP, which is the size of 8 right here. And the next thing that comes will be RIP. Let's give it a try. Let's run this once again. Let's go next. So we go 10 times for the password size. We go 8 times for the RBP, and let's use letters B for that. And letters C will be in RIP. Let's check it out. Letters B, which are 42, are in RBP, as we wanted, and letters C are in RIP, which we wanted as well. So we successfully control the value of RIP. But how can we actually get and run this function? Well, all we need to do is we need to put the address of this function inside the instruction pointer. And this instruction pointer will then afterwards execute our function because it's pointing to its address. How can we find out the address of the win function? Well, we can type disassemble win. Here it is, and here is where it starts. So to craft our payload, I will use a help of a small Python program that I have. So let me open a second terminal. Let me enlarge it just so we can see everything better. And let me nano pyx.py. Okay, so here is the address that I previously used, which in this case will be this one. So let's copy it. This is the address of the beginning of the win function. Let's delete it, paste it right here. And here we actually craft our payload. So notice we have 10 A's for the password, 8 B's for the RBP, and the thing that comes after should be the address of the win function, since that is what we want to run. Now, if we just use this address afterwards, it will not work. Let me show you why. If I type run, press yes, click next, and then just type 10 times A, 8 times B, and then I put this value right here, you will notice that RIP is some random value right now. It's not exactly this, and this is what we want to have inside of it. This is because we're specifying a string. We need to specify bytes instead. And there is also something called little and big endian, so we also must reverse it in order to make it work. That's why our payload should be these bytes right here reversed. So x40 is first one, or should I say last one in this payload, x11 is in the middle, and x90 will be right here. This is simply just this address reversed. Now, if I save this, close it, and run this program, it prints something weird, right? But this doesn't matter for us. All we want is this payload to be specified inside of this program as an input. We can also run this Python program from the GDB if we wanted to by using this command, R, and then 3 arrows to the left, then $, open brackets, python2, -c, and simply -c stands for specifying the command between these double quotes, which will then be executed with Python. And all we want to do is print our payload, which in our case is, we already know, 10 A's, 8 B's, and then our address, which we can specify by \x90, \x11, and \x40, if I'm not mistaken. Let me just cat the pyx.py, and here's the address. So 90, right here, 90 being the first one, we got 11 being the second or the middle one, and we got 40 being the last one at the end. Okay, so we specified the password, the RBP, and we also reversed the address of win function. Let's give it a try. All I need to do is close this with single quote after the print statement and with brackets at the end, and if I press enter, it will ask if I want to run from beginning. I will specify yes. Let's check the instruction pointers. So you will notice right now that nothing really happened yet, but if I type next, it will auto input our user input with our payload that we crafted with Python right here. Let's click next. And now if I type I and then R, we will see that RBP is overflown with Bs right here, but we will also see that RIP now has the address of the win function, which even says right here. So if we did everything successfully, if I type next, it should execute the win function, which, let's remind ourselves, prints you win. Let's give it a try. And here it is. It says you win. We successfully hacked this program to make it execute a function that it never really executes when run normally. We manipulated the registers, we manipulated the instruction pointer, and we put the address of this function in the instruction pointer in order for it to be ran. And we successfully did that. Now keep in mind this is a simple example, and we also turned off the stack protection, so in real life this is also a little bit harder to do than what we showed right here. But nonetheless, it's important that you understand in theory how this works. Okay, now that we covered all the known attacks that hackers perform, starting from running Trojans to a simple social engineering, from showing an example of a simple zero-day vulnerability, and in this case, if this was a program which is in use and we discover this vulnerability, it would be a zero-day vulnerability because this code has not been patched yet. Since we did all of this in details, let's also devote the next section into covering social engineering in details. And after that, we're pretty much done with this introductory part of the cybersecurity course, where we focus on different attacks and on hackers and vulnerabilities. See you in the next lecture.